Hey guys, here is the whole of C2 for AQA in only 29 minutes. Ionic bonding occurs between a metal and a non-metal. So something that is on the right hand side of the periodic table and something that is on the left hand side of the periodic table. If we use sodium chloride as an example, here we have sodium with 1 electron on the outer shell and chlorine with 7 electrons on the outer shell. What is going to happen is this electron here is going to go over there because everything wants to have a full outer shell. And what we are going to end up with afterwards, in square brackets, is chlorine and sodium having a full outer shell. Chlorine with its 7 original electrons and then the extra one it has gained from sodium. Now because sodium has lost an electron, it is going to have a positive charge, and because chlorine has gained an electron, it is going to have a negative charge. Metals are going to form positive ions and non-metals are going to form negative ions. And between these positive and these negative ions, they're going to build up this massive, massive lattice, and there are going to be really, really strong bonds in between them. There are very, very strong attractions. And because they have such strong attractions, this leads to their properties. So the properties are that they are going to have high boiling points because you're going to need a lot of energy to separate out these things. High melting points. When they are a solid, they are not going to conduct electricity, but they are going to conduct when molten or dissolved. And the reason they're only going to conduct when they're molten or dissolved is because this is when the ions are going to be free to move around. Now this is a tricky bit that they might throw on there. Now you may not have noticed on your formula sheet, may not have seen the formula sheet before, that there is a list of ions on there. And you're going to have things like your positive ions and you're going to have things like your negative ions. When you're working out the formula of ions, you need to make sure that overall you get a neutral charge. So here we have some positive and negative one. If you're making sodium hydroxide, we have a positive and we have a negative sodium hydroxide. However, if we're making sodium sulfate, because the ion for sulfate is 2 minus, what we're going to need to do is have 2 sodiums for every sulfate to give it a neutral overall charge. Covalent bonding is going to happen between non-metals. And this is sharing of electrons. Now there are a few common ones the exam board will expect you to know. This is hydrogen chloride. What you need to do is have your overlapping circles. Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons and then 1 from hydrogen. Make sure you have your overlapping circles and you draw your electrons in the middle. Methane, which is CH4, and carbon is going to have 1, 2, 3, 4, and then each of the hydrogens gives 1. Water, which is going to have an oxygen in the middle, hydrogens either side, 1, 2, 3, 4, 5, 6 from the oxygen, and then another 2 from the hydrogens, and ammonia, which is NH3. So we're going to have 1, 2, 3, 4, 5. 1, 2, 3. These are the simple molecules the exam board expects you to know about and expects you to be able to draw. When we're talking about simple covalent molecules, the exam board expects you to know the properties of them. So these are going to have low melting points, low boiling points, They do not conduct electricity. And they are generally going to be a gas or a liquid at room temperature. When we're talking about giant covalent structures, the examples gives are diamond, which is made of carbon, and silicon dioxide. Now you need to know the properties of these, and the properties are that they have high melting and boiling points. And they do not conduct electricity. Diamond and graphite are two examples of structures that are made purely from carbon, but diamond is going to make 4 bonds and graphite is going to make 3 bonds. So diamond, as I mentioned before, is hard, it is strong, it has higher melting points and boiling points, whereas graphite is in layers. Now, layers can slide, which means it is soft. And in between these layers, there are this extra electrons. So they have 3 electrons. So they can conduct. In metallic bonding, we have layers, which means they can slide. So a pure metal is going to be soft. And we have these positive ions, and then around them we have these 3 electrons. And this means they can conduct electricity. Now, pure metals have layers. Which means they can slide, whereas an alloy doesn't have any layers. You can see that big brown blob in the middle disrupting the layers. If there is no layers, there is no sliding. If there is no sliding, it makes it harder, which means alloying a metal improves its properties, is going to make it much more useful for things. The last type of metal you need to know about is shape memory. And that just means it can remember its original shape. So if it becomes deformed, say if you break your braces or you sit on your glasses, it can easily go back to its original shape. Plastics as polymers are incredibly useful things, and there are 2 different types you need to know about: thermosetting and thermosoftening. Now, thermosoftening polymers are all these mixed up chains. They are just tangled together. Thermosetting have these crosslinks, which means their properties are going to be a lot different. When we have these crosslinks, it is going to be rigid, and it is going to be heat resistant, which means it's going to be the type of plastic that's going to burn when you heat it, whereas thermosoftening is just going to melt. Nanotechnology is technology that is very, 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 very small, and this has some advantages. It means it can get into the body easier. So we can use it for things like delivering drugs. or sun cream. That is a very, very common example. Very, very small. Now the problem with nanotechnology is that it's only been around for a few years, so we don't know what the long-term impact is going to be. Here we have an element from the periodic table, and this number up here is the mass number. This one down here is the atomic number. Now the atomic number is going to equal the number of protons, and the mass number equals the number of neutrons plus the number of protons. So if you want to find the number of protons, we just look at the atomic number down here. If you want to find the mass number, or if you want to find the number of neutrons, we need to do the mass number minus atomic number. Now there are 3 subatomic particles that you need to know about. I've mentioned 2 of them. Neutrons, protons, and electrons. Neutrons and protons have a mass of 1 and electrons have a mass of 0. Isotopes are a different version of the same element. So here we have hydrogen, and the atomic number of all of these is 1. That tells us it has 1 proton, and the proton is the bit that identifies the elements. And then if we look at the masses, you can see we have a mass of 1, a mass of 2, and a mass of 3. So this tells us that this one here is going to have just 1 proton. This one here has 1 proton and 1 neutron, and this one here has 1 proton and 2 neutrons. Just because we change the number of neutrons something has doesn't change what it actually is. Now there is a lot of maths in this unit. I've written a book that's going to help you through all of the maths if you get stuck on any of these bits coming up. First of all, we're going to look at relative formula maths, and you need to use your periodic table to work out how much each of these things weigh. So hydrogen, we have 2 of them, they weigh 1 each. We have sulfur, we have 1 sulfur and it weighs 32. And we have 4 oxygens and they weigh 16 each. If we add all of those together, we are going to get a mass of 98. If we wanted to work out the percentage of, say, sulfur in this, we would just take the amount for sulfur, which is 32, and divide it by 98, times it by 100 to get our percentage. Empirical formula is for the higher tier only. Now the way that I'd like you to solve these is by writing down the elements, writing down the number in the question, and it doesn't matter whether this is a percentage or whether this is a actual number, it doesn't matter. What you need to do then is to write down the mass, so that is 12 and 1. You need to divide these numbers by each other, so that is going to give us 6.25. And then 25 divided by 1 is going to be 25. You need to divide this by the lowest number, which in this case is 6.25. So 6.25 divided by 6.25 equals 1. And then we need to do 25 divided by 6.25, which is going to give us 4. So the empirical formula for this would be CH4. Now these questions are tricky, they do come up a lot, and again in my book on this topic I have loads and loads of practice calculations for you. Just go to my website and you can download it there. This is another maths bit that's just for the higher tier students, and I think this is potentially one of the trickiest things in there. It's reacting masses. So we need to work out how much hydrogen peroxide we're going to produce if we have 8 grams of oxygen. Now the way that I do this is to start out by working out the masses of everything. So oxygen, we have 2 of those and they weigh 16 each, that weighs 32. Over here we have 2 times hydrogen, they are 1 each, so that is 2. 2 times oxygen, they are 16 each, so that is 32, giving us 34, and we have 2 of them, so that is going to give us 68. So we know that if we had 68 grams, rather we know 68 grams would be produced from 32 grams of hydrogens, and now we can just treat this as a ratios question. What we need to do is 8 divided by 32, that is going to give us 0.25. We can then take that and times it by 68 over here. So 68 times 0.25 is going to give us 17 grams. Loads more examples again in my book. More maths here, and again just for higher tier, but this is actually really nice because it's just a simple division. To work out the percentage yield, you need to look carefully in the question, work out how much was actually produced, and just divide that by theoretically how much should have been produced. Now they could ask you why the maximum amount wasn't produced, and this could be because it is a reversible reaction. And the symbol for a reversible reaction is just these little backwards and forwards half arrows. We can use chromatography to separate out substances. What we have down here is a solvent, that's the mixtures, the substances dissolve in, and then they move up through the paper. Here we have a pencil start line, and it has been penciled because otherwise the pen would dissolve in the solvent and then you would just get a massive smear. But I quite like chromatography because it's pretty. Other ways of separating things out are gas chromatography. So you feed a sample into an oven where it gets heated up and turned into a gas. It will then get fed into a computer, and the computer will tell you what things are. Mass spectrometry will separate things based on mass, unsurprisingly based on the name, and what you'll get is lots of different peaks depending on the size of something. Now these modern techniques are better than previous techniques because they're very accurate, they are sensitive, they are quicker. You can use small amounts, so you don't have to have loads to be analysed, but the disadvantages are that they are expensive and a special lab needs to do them. Two really common ways of measuring a rate of reaction are looking for a colour change, so in sodium thiosulfate looking for it to go cloudy, or in the iodine clock looking for it to go black, or collecting gas. Now you can collect gas by inverting a measuring cylinder over a washing up bowl full of water, or you can measure the loss of gas by putting it on a scales and watching the mass go down, or you can use a gas syringe. So there are lots of different ways that you can actually watch a rate of reaction as it is happening. You can watch for a colour change, and if you wanted to improve that, you could use something like a data logger and to actually measure the colour change or the cloudiness as it was going along. Or you can just measure the gas collected over a certain period of time or over a certain, over the whole experiment. There are several parts of collision theory you need to know about. We're going to start with temperature. So there are two important things you need to know about temperature: how fast they're moving and whether there is a successful collision or not. Now, things that are moving slowly around aren't really going to be doing very much. They're kind of just lazily wandering around. So they're not going to find each other as quickly, and when they bump into each other, they might just go, meh, and then wander off in the opposite direction. Whereas things that are whizzing around really, really quickly, in lots and lots of different directions are much more likely to first of all bump into each other, and then when they bump into each other, there is much more likely to be a reaction that takes place. So two things: the frequency of collisions and the number of successful collisions. When we're talking about concentration or pressure, because in this circumstance we can treat them the same, it's a low concentration. There aren't very many particles around, so it doesn't matter how fast they're moving. If they can't find another particle to collide with, to react with, they're not going to react. At a high concentration, when there are lots and lots of particles around, it is much more likely that they are going to find something to collide with and thus have a successful collision. Now, a catalyst doesn't actually get involved with the reaction, it will just speed it up. So in our uncatalyzed reaction over here, all of the particles are whizzing around all over the place. It's very, very hard for them to bump into each other and react. Whereas with our catalyst, they are stuck in one place. So if something was to whiz along and bump into them, instead of in the uncatalyzed reaction, whizzing along and maybe bumping into this one, whizzing along, it's much easier for it to bump into the catalyst because the catalyst is a lot bigger. Now, surface area is tricky to understand because the smaller the particles, so if something is powdered as opposed to in a lump, this is going to have a larger surface area. Now, only the things on the outside can collide. So in the lump, there is only 10 different particles available to collide. Whereas here, all of them can react with other things because they're all spread out. So they have a larger surface area. Endothermic and exothermic are very complicated words for gets cold and gets hot. And if we think about this in terms of energy, so if we say something is exothermic, it gives out heat, and something that is endothermic takes in heat. If we want to make this a bit more sophisticated and talk about energy, we can just replace the word heat with energy. So something that is endothermic takes in energy and something that is exothermic gives out energy. On the pH scale, 1 is something that is very acidic and 14 that is something that is very alkali. Now, acidity comes from hydrogen ions and alkalinity comes from hydroxide ions. And what we get is hydrogen ions plus hydroxide ions turn into water, which is neutral. Now this comes up a lot, so you should definitely learn that equation. It's lovely, it's simple, you should learn it. They love asking about practicals, not only the rates of reaction practicals, but by making salts. So here we have some hot sulfuric acid, we've added in copper oxide and we've stirred this until the black powder won't dissolve anymore. We need to filter it to get rid of all the black powder, so that'll stay up here and we will get a lovely blue solution come down here. Then what we need to do is to evaporate all of the water off so that we end up with the copper sulfate crystals. There are several general equations you need to know. So acid plus metal is going to be a salt and hydrogen. Acid plus base, salt and water. Acid and metal oxide, salt and water. Acid and metal carbonate, salt, water and carbon dioxide. If they ask you about state symbols in the exam, it is time to take note because it means they are probably looking for a gas or a solid being produced. If you add two liquids together, look to see whether one of the products is a solid or a gas because that's the sort of thing they're looking for in the answer. Liquid generally is just going to be water. AQ is aqueous, which means something dissolved in water, and there is another one, PPT, which is precipitate, which means it goes cloudy. If you see something after it which is produced as solid, you can say it goes cloudy. Gas, you are going to get bubbles. In electrolysis, you are going to get the negative ions going towards the positive electrode and the positive ions going towards the negative electrode. At the negative electrode, the positive ions are going to pick up electrons. At the positive electrode, the negative ions are going to give up electrons. And we can think about our oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. When we have the electrolysis of aluminium oxide, or trying to get aluminium, it looks ever so slightly different. So we have negative oxygen ions. These are going to go to the positive electrode. Now these positive electrodes are made of carbon. When we add oxygen into carbon, we get carbon dioxide. So these positive electrodes are actually just going to turn into gas and then go away. The negative electrode is this whole thing all around the outside, and then the positive aluminium ions are going to go towards the negative electrode and come out the bottom here as aluminium metal. In the electrolysis of brine, we have a lot going on. So we have sodium chloride solution. Now we are going to have chlorine ions. These are going to go towards the positive electrode, and these are going to turn into chlorine gas. Now because this is a solution, we are going to have hydroxide ions, and we are going to have hydrogen ions, and we are going to have sodium ions as well. Now the hydrogen ions are going to go towards the positive electrode. These are going to be turned into hydrogen gas, and then we have the sodium and the hydroxide left over. These are going to turn into sodium hydroxide, which is bleach. When we want to electroplate something, we can charge it up, and then the positive ions of the metal are going to come along to the negative electrode and slowly build up on there. So we can take something that is, say, silver, coat it so it looks like gold, so it will look much, much prettier, and then it will be worth more money to people that are selling it. Well done guys, that was the whole of C2. Excellent work for making it this far. Any questions you've got, leave me a comment below and I'll do my very, very best to answer them for you.